everyone, and welcome to Unit 2, Lesson 5 on grams, moles, and representative particles. Today what we're going to do is build on what we did in our previous session, converting between grams and moles, and now expanding that into particles, which could include atoms, molecules, and formula units. We're going to begin, however, by going over the homework from the grams and mole conversion. So if you look at the first page here, we have our first question was how many grams are there in 2.3 moles of silver? So if you notice, I have 2.3 moles of silver. We're always going to put whatever we start with as our starting point over here from the problem. And in this case, because we're just talking about a single element, we don't have to actually worry about any type of molar mass addition. So we're just going to get the average atomic mass for silver straight off the periodic table. That turns out to be 107.87 grams. When we multiply, because it's on top, we wind up with this answer, 248.101 grams. And then accounting for significant figures, that becomes 250 grams of silver. In our next question, it says, how many moles are there in 742.56 grams of lead-2 nitrate? Don't worry about the name so much right now. So the first thing that you want to do is add together your compound. Notice we have 2 outside the parentheses, which means we have 2 nitrogens and 6 oxygens. So this mass right here, 28.02 grams, is the mass for 2 nitrogens, and this mass is the mass for 6 oxygens. Because grams is our starting point, we want to put grams on the bottom of the first equation in order for it to cancel out. Multiplying by 1 is not meaningful, so you can skip that part. So in this case, we're just going to take our 742.56 divided by our 331.22 to get our final answer. Notice also that we have 5 significant figures in the problem, 5 significant figures in our answer. In our third question, again, we had to add up to get the molar mass of H2SO4. This time we're starting with moles, so moles go on the bottom. We're going to take 3.567, multiply it by the molar mass. We get this answer, 349.9 grams of sulfuric acid, or H2SO4. In our fourth problem, we have CuNO32, or copper-2 nitrate. Again, we're going to get the mass of copper-2 nitrate. Then since we're starting with grams and we want the unit of grams to cancel out, we're going to put grams on the bottom and moles on top. Notice that our final answer has 4 significant figures. And finally, for problem number 5, a second problem where we had just an element, so we didn't have to calculate a molar mass. We could just get the molar mass of copper straight off the periodic table. So 150 grams from the problem divided by 63.55 grams per mole. And we wind up with this answer of 2.360 moles. If you're wondering how to do the strike through, you're going to hold down Shift, hit Alt, and then the number 5, and that will allow you to draw a strike through or a line through your units so you can clearly show which ones are crossing out. I would also appreciate it if you could highlight your answer, because that makes it a little bit easier for me to find on some of your papers. Okay, so this is what we did in our last class. If you notice, we went between grams and moles, and we used molar mass as kind of our bridge between grams and moles. Today, what we're going to do is we're going to expand on that idea of grams and moles, and we're going to use Avogadro's number. And Avogadro's number is going to be the bridge to 2 different locations. So if I'm going between moles and atoms, because I have a single type of element, I'm going to use Avogadro's number per mole. If I'm going between moles and molecules, or moles and formula units, again, I'm going to use Avogadro's number of molecules or Avogadro's number of formula units per mole. Finally, the last conversion all the way on the side here is just going between molecules and individual atoms. So one of the things that we're going to practice, first thing that we're going to practice actually is knowing when we have to use this pathway and when we can use our shortcut. So let's take a look at some scenarios. So I wrote up here, can I take the shortcut to or from atoms? So by shortcut, I mean this arrow down here that allows us to go directly from moles to atoms. So in our first example, we're talking about copper. Copper copper is an element on the periodic table, and we're going to copper. So we're talking about a single element for the entire time. If we are talking about a single element for the entire time, we can take the shortcut. So we can go from atoms of copper to moles of copper. So the answer to the first one is yes, I can take the shortcut. For the second one, it says convert 50 grams of copper 2 nitrate to atoms of copper. So in this case, I'm starting off over here with grams of copper 2 nitrate. That's an ionic compound. So I can go from grams to moles, but I cannot go directly to atoms. So in this case, I have to go up to formula units first, and then I can convert to atoms afterward. So the answer here is no. Letter C, convert 5 times 10 to the 24th atoms of copper to grams of copper 2 nitrate. Again, I have a compound right here, just like I had a compound up here. Anytime that you have an ionic compound like this, you cannot go directly between atoms and moles. So I'm starting off with atoms of copper, and in this case, I'm going to have to go from atoms of copper up to formula units before I can come down here and go to moles and eventually grams. So this is also a no. Finally, with letter D, it says convert 3.50 times 10 to the 24th atoms of aluminum to grams of aluminum. Because I'm just dealing with aluminum, atoms of aluminum and grams of aluminum, I can take the shortcut here. A single element by itself is the only time that you're able to take that shortcut. So, an easy way to think about this is to look at your problem and decide, do I have a single element at the beginning and at the end? If you have a single element during the entire course of the conversion, you can take the shortcut. Otherwise, you're going to have to go up to molecules and formula units before you can either go down to moles or atoms. So here is our first example. It says how many atoms of chlorine are contained in 250 grams of copper 2 chloride. When you are doing this problem, what I would like you to do is to show your molar mass work. You're not required to, but it would help me out when I'm grading your papers on the side. Plus, if you make a mistake adding it up, you'll at least earn some partial credit. So, copper 2 chloride. The mass of copper is 63.55 grams per mole. The mass of chlorine is 35.45 grams per mole. We need to multiply that by 2. So, I'm going to use my calculator here. So, we'll have 35.45 times 2. So, that's 70.90 plus. We're going to add on the copper, 63.55, and we get a total mass of 134.45 grams per mole. Now I can set up my problem. I have 250.0 grams of CuCl2, and in this case, I'm going from grams all the way to atoms. So going from grams to moles up to, because I have a compound, formula units, and then down to atoms, that's 3 different conversions. Every time you cross one of these yellow arrows, that is a conversion factor. So if you would like to plan ahead, draw out the number of conversion factors that you will need. So let's go back to look at our problem. We're going to need 3 conversion factors before we get to our final answer. So the first one is going to have us convert from grams to moles. So I'm going to take the 134.45 grams. We're going to put that on the bottom. That is the number of grams in 1 mole of CuCl2. That will allow me to cross out my unit of grams. So grams is now gone. In my second conversion, if I go back to my map, I've just gone from grams to moles. Now I have to go up to formula units, and I'm going to do that using Avogadro's number, 6.02 times 10 to the 23rd. So In this case, I have 1 mole CuCl2 on the bottom, 6.02 times 10 to the 23rd formula units, CuCl2 on top. Finally, in the last section, if you look at our map again, I'm right up here with formula units, and I want to go down to atoms. The number of atoms per molecule or formula unit. So the number of atoms per formula unit. So in this case, every formula unit, copper CuCl2, I have 2 atoms of chlorine. So 2 atoms of chlorine for every 1 formula unit of CuCl2. I can go ahead and cross out my units. So moles of CuCl2 will cross out, formula units of CuCl2 will cross out, and now I'm left with just atoms of chlorine. So if I type this into my calculator, 250 divided by 134.45 times 6.02 e to the 23rd times 2, I get an answer of 2.238750 times 10 to the 24th atoms of chlorine. But of course, I need to look at significant figures. So I have 4 significant figures here. I have 5 here, but I only have 3 here. So anytime we're using Avogadro's number, we're going to be limited to 3 significant figures. So in this case, my final answer is going to be 2.24 times 10 to the 24th atoms of chlorine. Okay, if we look at our next slide, example 2. How many grams of sodium carbonate can be produced from 2.50 times 10 to the 24th atoms of oxygen? So 2.50 times 10 to the 24th atoms of oxygen. In this case, we are starting off with atoms and we are working backwards in order to get to grams. So we're starting off down here and we're working backwards to get to grams. Because the compound is not just oxygen, because it's sodium carbonate, I have to go up to formula units first, down to moles, and then across to grams. So it's again going to be 3 conversions. So the very first thing that I'm going to do, I'm going to get the molar mass of Na2CO3. So I'll have 22.99 grams per mole for sodium, and multiply that by 2. I'm going to have 12.01 grams per mole for my carbon. And then finally, my oxygen, 16 grams per mole, which again, I'm going to multiply in this case by 3. So adding this together, 22.99 times 2 plus 12.01 plus 16 times 3 is 48. So I have 105.99 as my molar mass. Not ready to use that just yet. So going back to my conversions, the very first thing I want to do if I'm here in atoms is I want to go up to formula units. So it's the number of atoms per formula unit. So in this case, I have 3 atoms of oxygen. 3 atoms of oxygen goes on the bottom. That way it'll cross out with atoms of oxygen up here. For every 1 formula unit of Na2CO3. The next part, I can cross out my atoms of oxygen. And if I look back at my map, I'm now up here. So now I'm going to go down to moles, again using Avogadro's number. So 6.02 times 10 to the 23rd formula units of Na2CO3 for every 1 mole of Na2CO3. Right now, anytime we are using moles as part of a conversion factor, it's always going to be 1. Later in the year, that will change when we start looking at balanced equations. But for today and for the next couple of weeks, anytime that we're converting to or from moles, we're going to use 1 mole per number of particles or 1 mole per number of grams. This allows me to cross out my units of formula units. And finally, for my last conversion, I'm ready to use my molar mass. So I'm now at moles, and I want to go to grams. So I'm going to use my molar mass. And this time, grams will be on top. 5.99 grams of Na2CO3. And that's for every 1 mole of Na2CO3. That will cancel out units of moles. That will drop out there. Typing this into my calculator, I'm going to get 2.5 e to the 24th divided by 3, because it's on the bottom, divided by Avogadro's number, 6.02 e to the 23rd, times 105.99. And I wind up with an answer of 146.7192 grams of Na2CO3. But again, we're going to be limited to 3 significant figures. So it's going to be 147 grams of Na2CO3. Alrighty, in our third example problem, it's going to be fewer steps because we're not going all the way to atoms. So if you read the example problem, what is the mass of 3.45 times 10 to the 23rd molecules of CCl4? In this case, we will need to get the molar mass of CCl4, so we can start by doing that on the side here. So carbon is 12.01 grams per mole, and chlorine, this is off the periodic table, is 35.45 grams per mole. We're going to multiply that by 4. So if I take 35.45, multiply that by 4, add on my carbon, so I get a mass of 153.81. I'll use that later. Right now, what I need to do is convert from molecules of CCl4 to moles. So if you look at the chart, right now I'm up here, starting at molecules, and I want to get to grams. So I need to come down this slide here between molecules and moles using Avogadro's number. So only going to be 2 conversions. And on the first one, remember, we're going to put Avogadro's number times 10 to the 23rd. In this case, it's molecules of CCl4. And I apologize, there is no shorter abbreviation for the word molecules. On top, we're going to have 1 mole of CCl4. This will allow me to cross out my units of molecules of CCl4. And now for the next part, I can use my molar mass to get to grams. So 153.81 grams of CCl4, that part goes on top. And then 1 mole of CCl4 will go on the bottom. I can now cancel out moles of CCl4, so that part will drop out. Now I can calculate my final answer. So into my calculator, I'm going to type 3.45 e to the 23rd divided by 6.02 e to the 23rd times 153.81. And I wind up with this answer, 88.1469269 grams of CCl4. But of course, 3 significant figures here and here. So my final answer is simply 88.1 grams of CCl4. For our fourth and final example problem, let's take a look. How many atoms of gold, notice that it's just an element by itself, how many atoms of gold are contained in 560 grams of pure gold? So we're starting off with grams. We're going to go grams to moles. And now we can use the shortcut down to atoms because we're only talking about gold. It's not part of a larger compound. So in this case, I'll have 2 conversions in this problem. So let's take a look at the problem. We have 560.00 grams of gold times 2 conversions. The molar mass for gold, when you look it up, is 196.97. And that is the mass for 1 mole of gold. Again, as a reminder, for the next couple of weeks, whenever we're going between mass and moles, or between moles and particles, molecules, formula units, or atoms, we're going to use 1 mole. Next part. Going from moles of gold, which is right here, to atoms of gold, we're going to use Avogadro's number. So 1 mole of gold, 6.02 times 10 to the 23rd atoms of gold. Typing this into my calculator, I'm going to get 560 divided by 196.97 times 6.02 e to the 23rd. So I get an answer of 3 significant figures, 1.71 times 10 to the 24th atoms gold. As a reminder, for homework, I would like you to try problems 1 through 5 on the grams, moles, and representative particles assignment. There are 8 additional problems on that page. You don't have to do those. However, we might be using some of them for enrichment in my next video. So if you would like to try some extra problems, I can provide the answers to those last 8 or 9 problems if you would like. Otherwise, I hope everyone has a great week. Thanks, everyone.